Hey there, astronomy students. This is Ms. Ruark. We are in chapter 14. This is podcast 14.1, where we talk about neutron stars and pulsars. All right, so what is a neutron star? Well, when a supernova explodes, the core is going to collapse into a very small size. Now remember, a supernova is when a large star, massive star, explodes. Okay, if that collapsing object has a mass greater than 1.4 solar masses, it's beyond the Chandrasekhar limit and will not become a white dwarf. Okay, so that's a small one. If it instead it collapses into a black dwarf. Well, if the mass of the collapsing star happens to be between 1.4 and 3 solar masses, it can halt its contraction and form what we call a neutron star. And theory predicts that inside of a neutron star, what happens is the protons and electrons combine to form a degenerate neutron gas. Okay, so anytime you have a supernova explosion of a solar mass that's greater than 8 solar masses, the star blows away its outer layers, right? And it contracts. Well, if it contracts to 1.4 or less, it becomes if it contracts to less than 1.4, it becomes a white dwarf. If it contracts to a little bit greater than 1.4 and it can't halt the contraction, it becomes a black dwarf. If it's between 1.4 and 3, it can halt the contraction and becomes a neutron star. Oh, so many things to remember, right? Okay, so I just said that. Okay, and I just said that. Okay. So just to show you, this is kind of an idea as to what happens to these stars. So you might want to pause this for a second and write this down, because this is important. If it's a supergiant, heavy atom fusion is going to happen. It's going to become a supernova, so it's going to explode really big, and it can become one of two things, a black hole or a neutron star. Yeah. If it's a giant, the helium flash happens, it turns into a planetary nebula, and then it becomes a white dwarf. Okay, so if it's a supergiant and it loses a lot of mass, it can actually come over here to go through the white dwarf stage. But if it doesn't, then, well, it's one of these two. Dun, dun, dun. Okay, typical properties of neutron stars. They're roughly about 10 kilometers in radius. They're going to spin really fast because they conserve angular momentum as they contract. They have high temperature, powerful magnetic fields, and they have a mass of about 1.4 to 3 solar masses, and they're extremely dense. Okay, so how dense are they? Well, if you had a piece of neutron star, the matter the size of a sugar cube, a sugar cube, they're teeny tiny. Well, they're not teeny tiny, but you put them in your tea, at least they used to. It has a mass of about 100 million tons. It's huge. Man, that's dense. Okay, so a neutron storm more than the mass of the sun would comfortably fit within the capital beltway. So the capital beltway is the beltway, or the, in case you're not familiar with it, it's the, I guess we wouldn't call it an interstate. It's like a highway that goes around Washington, D.C. Yeah, not very big in the grand scheme of things. All right, so discovery of pulsars. How do we know that they exist? Well, we know that that neutron stars exist when they discovered the pulsar. So pulsars are spinning neutron stars that rapidly emit radiation, and they were discovered in 1967. As they spin, they emit beams of radiation from their magnetic poles that sweep across space. And these pulses are detected if the beams happen to sweep over the Earth. Okay, so what happens? It's spinning. And why is it spinning? Because angular momentum is conserved. It collapses. The core spins up to a period of a few milliseconds. Magnetic fields are amplified, and that's where these pulses, or these beams of radiation, are coming out of the magnetic fields. Pulsar periods and winds. So over time, the pulsars are going to lose their energy because it's being given off through its magnetic poles, and they're actually going to slow down. They're going to lose their angular momentum because their energy is leaving them and going into space. Right? The energy that they're giving off, or that they're emitting, it's beams of radiation that comes off of their magnetic poles, and it sweeps. it's carried away as pulsar winds and jets of high energetic particles. All right, and these are just some examples of different pulsars here, and the rings and jets that are produced by their pulsar winds. Okay, this is just a picture of this that's been amplified. Here's another one, the pulsar here, and this is the wind and nebula, and then this is the remnant of a supernova that was left over. Here's another pulsar here. Here's another pulsar magnified. You can see the pulsar motion. The wind is going through space this way. All right, these winds carry around 99.9% of the energy released from the slowing down of the pulsar's rotation. All right, so think of a pulsar as a lighthouse. Okay, a lighthouse. There's a picture of it here. Okay, so a pulsar's magnetic field has a dipole structure just like Earth. It has a top and a bottom, and the energy is given off, or the radiation is emitted along those magnetic poles, similar to how a lighthouse gives off its light going off from two sides. Okay, and similar to, if you think about it as the Earth, we have the North Pole and the South Pole, right? Well, that's how the pulsar gives off its light. Images of pulsars. Here's some different pulsars that they have. Let's go back to this one. This one right here, there's your neutron star with all of its glory around it. Here's another one from the Hubble Space Telescope. Here's your neutron star. Oh, so cute. Let's see. The Vela pulsar moving through interstellar space. That was the one that we saw earlier. And here's the Crab Nebula. Its pulsar is here in the middle. The Crab pulsar, I just showed you that the Crab Nebula has a pulsar star in it, and it's a remnant of a supernova that was observed in 1054. Okay, here are the pulsar winds and the jets that are coming off of that pulsar. There's the jets. All right, more pictures of the Crab pulsar, and it's so pretty. I know. All right, and light curves of the Crab pulsar. You'll notice that as we see the light hit, this goes up and then it goes back down. It comes back up, and it says that this pulsar blinks twice each cycle. All right, so here variation in X-ray intensity. So we've got more X-rays coming off than we do light, visible light. All right. Let's see. Oh, I don't think I said too much about this on yours. Some neutron stars are moving rapidly through interstellar space. This might be a result of, and I don't know how to say that word, during the supernova explosion forming a neutron star. Okay, so moving on. Binary pulsars. All right, dozens of pulsars have been found in binary systems, allowing astronomers to estimate the masses of the neutron stars. Some form binaries with other neutron stars, and some will form binaries with black holes. Ah, pretty cool, huh? All right. Let's see, radial velocities resulting from the orbital motion lengthen the pulsar period when the pulsar is moving away from Earth. So it's going to seem like it's being redshifted, and shorten the pulsar period when it's approaching Earth. So we would say that it seems to be blue shifted if we were talking about it in terms of the Doppler shifting. All right. Neutron stars in binary systems. So we can have the X-ray binaries, and here's an example of an X-ray binary where we have a neutron star here in a binary system, and look, it's forming an accretion disk. Oh my goodness. Okay, so in some binary systems, mass flow in a hot accretion disk around the neutron star and causes the emission of X-rays. Okay, so here's your X-ray beam that's coming off in both ways, right? All right, so it can cause X-rays. And, oops, didn't mean to go that far. The fastest pulsars, which are the millisecond pulsars, appear to be old pulsars that have been spun up to a high speed by mass flowing from their binary buddies. All right. Okay, some pulsars can be found with planets orbiting them. That's pretty cool. So planets have been found orbiting at least one neutron star. They may be the remains of a companion star that was devoured by a neutron star. And they're discovered through variations of the pulsar period, which is caused by the wobble that's induced by the planet's orbit around the pulsar. Okay, so as the planets orbit around the pulsar, they cause it to wobble. and it results in slight changes of the pulses that we see here on Earth. And I just thought that because we were talking about neutron stars, it would be really cool to bring back an oldie but a goodie, Jimmy Neutron. All right, I'll see you in class.